Significant digits, a general science topic and a short crash course. What are significant digits and how are they used? Well, when is enough enough? Let me give you an example. I have a calculator here and I try to solve the following problem. 28 divided by 17. Fair enough. If I push the equal sign, this is the number I get. Holy smoly, it fills the whole calculator. Well, which of these many numbers would you actually write down as an answer? The whole thing? I don't think so. There must be a way of figuring that out, how much you need to write down and what the correct answer would be. Well, let me give an introduction to significant digits. There are certain rules attached to it. Rule number 1. Any digit that is not a zero is always significant. So 1s, 2s, 3s, 4s, 5s, and so forth. These are always significant digits. Rule number 2. Leading zeros in a number are never significant. Let me give you an example. How many significant digits do you have in 0.5? Well, 0 is a leading digit. That is not significant. So I have only one significant digit in that number. What about 0.0324? Again, my 0.0 are leading zeros. They are never significant. Hence 324 gives me 3 significant digits. 0.0024. Answer is 2. And what about this number? Well, the leading zeros are never significant, hence only the 6815 part is significant, and I have 4 significant digits. That satisfies rule number 2 and rule number 1. Rule number 3. Trailing zeros only count if a decimal point is actually present. What does that mean? Well, let me explain. How many significant digits are in 500? Well, these trailing zeros would only count if there's a decimal point, but I don't see one. Hence, 500 has only one significant digit. But what if 500 has a decimal, like 500.0? Well, now there is a decimal present. Hence, I have 4 significant digits. Why? Well, the decimal point makes all the difference. Let's take another number. What about 26,000? There is no decimal point, hence my trailing zeros are non-significant, and I have only 2 significant digits. Well, rule number 4. Zeros that are neither leading nor trailing are always significant. What does that mean? Another example. How many significant digits are in 5.05? Well, that 0 is neither trailing nor leading, but is sandwiched between 2 significant digits. Hence, it becomes significant. I have 3 significant digits in that number. What about 5.050? Well, a decimal is there, and as soon as a decimal shows up, and the zeros, they are all significant. Here you have it, 4 of them. Again, a decimal point makes a difference. What about 30,002? Well, those zeros are neither trailing nor leading, but are sandwiched between 2 significant digits. Hence, they all are significant. What about 1020.0? There's another decimal. Hence, 5 significant digits in that number. Alright, now that we have identified some significant digits and the rules that go with it, why do we care? Well, here's the deal. In science, we measure things. And reading measuring devices is where we need to be sure how many digits we can write down. What are the significant digits that I can write down as I read them off from an instrument? Let me give an example. Number of significant digits equals the digits that I can read off for certain of this instrument plus one I have to estimate, which is somewhat uncertain, a final uncertain digit. This uncertain digit is also called the fuzzy digit, because it is not quite exactly on, but we can estimate that it's probably pretty close. Well, let's read a ruler and see which digits are certain and which ones are my fuzzy digits, which gives me the significant digits for reading that instrument. Alright, here's a very coarse ruler. It is only centimeters, and there's a blue bar. What is the length of this blue bar? Now, which ones are the certain digits? Well, I can read 2 for sure, but it's a little longer than 2. However, since there's no calibration or scale past the 2, other than the 3, which is quite a distance away, I have to sort of estimate what that other number might be. That is my fuzzy digit. So, my fuzzy digit is a little more than 2, about 0.3 or so. Put them both together, and this is the number I would record, 2.3. This ruler gives me a resolution of 2 significant digits. Well, what about if I change the ruler a little bit? Here's one with much finer increments. The blue bar is still the same length. Let's see what we can do now. Which digits are actually certain I can read for sure? Well, there is a 2, and now there's definitely the 0.3, because I can see absolutely that this is the length of my blue bar. But the blue bar extends a little bit beyond the 0.3. Again, there's no subdivision past that point, so I have to estimate what this might be. Well, what do you think the fuzzy digit is? Well, I came up with about 0.03. You might come up with a slightly different number. This will be my fuzzy digit, and this is how good I can read the ruler. So what number would I record? I can write down the measurement for this ruler to be 2.33. My ruler is accurate to 3 significant digits. Well, there are some more instruments we can read. Let's kind of read the certain and the fuzzy digits of the following. Here's some graduated cylinders with some liquid in it. You know that you read the graduated cylinder at the curve of the meniscus, like right here. Well, which number would you record? Which numbers are certain, and which ones do you have to guess? Well, I would write down 8.35. The 8 is a definite. The 3 subdivisions are also definite and certain. Well, the other ones, it's right in the middle between those two, so I guess that's about half, or 0.05, and I can write this down. I can read that graduated cylinder to 3 significant digits. What about if my meniscus goes upward? Well, same rules apply. What would that number be? Well, how about 8.65? Yes, 8 is definite. The 6 subdivisions are definite, and the 0.05 is my fuzzy digit. Now let's do one more. What about the last graduated cylinder, right here? Which number would you write down? Well, you might be tempted to say, well, this is 8. Really? We have been able to read these graduated cylinders before to 3 significant digits. If you just wrote down an 8, that would mean that you have a very inaccurate graduated cylinder that can read only 1 significant digit. But we've seen it is not the case. So which number would you actually write down if it's exactly an 8? Well, 8.0? I can write one more, because we were able to read to 3 significant digits, and the number you need to record is 8.00. Why is that important? Because if you present your data to somebody else, and you just write down the 8, they may think you have a very inaccurate graduated cylinder. Now, writing down 8.00 gives the reader the indication that, oh, this graduated cylinder is somewhat calibrated, so you can read it much more precisely. What about this instrument? Can we read it if we, of course, take a measurement with it? And here it is. My little hand has moved past the 4 close to the 5. Well, as you can see, the scale here is subdivided into quarters. Hence, 4.75 would be an acceptable answer for that one. I cannot read anything beyond it, so again, 3 significant digits for this particular instrument. Now, we can go a step behind measurements, and that is doing some calculations with our measurements. But there is a very, very important rule. My calculations cannot never improve the accuracy or precision of my measurements. With other words, now significant digits are absolutely essential. Here's an example. Let's say I want to get a volume of an object that I have measured. It looks like this is a brick with a length of 3.10 centimeters on one side, 4.102 centimeters on the other side, and 8.3124 centimeters on the last side. As you can see from the numbers, it looks to me like I have used 3 different rulers, with the first measurement being the poorest, and the last one with 5 significant digits being the best. Now I need to multiply them together. But what would I record? Well, I would actually write down 106 cubic centimeters. Why is that? Because we need to go by the weakest or lowest number of significant digits in our calculation, the 3.10. This number has only 3 significant digits. Therefore, my answer cannot exceed 3 significant digits. It is the poorest link in our chain. And 106 is the rounding I need to do to write that answer down correctly. Let's do a division. For example, if we calculate density, I measure a mass of 7.9321 grams, which means my scale was fairly accurate, probably an analytical balance. Now I divide volume into it, 0.98 milliliters. That's not quite as good. What would I write down as my answer for gram per milliliter or gram per cubic centimeter? Well, I have 2 significant digits in my weakest link. Therefore, my answer cannot exceed 2 significant digits. And I need to round it to 8.1. No matter how precise I did the mass measurement, I need to go with the weakest link. What about if we go ahead and do addition or subtraction? Well, then the rule is a little bit different. Here is the precision of sums and differences. In order to add things up, like in this example, line up the decimal point and see how many digits past the decimal point are actually there. As you can see in the last number, the 15.9994, a digit is kind of missing. Well, we don't go past that missing digit. We stop again at the, if you want to, shortest tail. And so my answer needs to be 18.0153 and not a digit more. What about subtraction? Here's another example. 73.01234 grams. That's a pretty good measurement. Subtract from this 72.014 grams. There are 2 digits that are too short. Again, line up the decimal points and don't go past the shortest of those. The answer should be 0.998. If this wouldn't be enough, rounding while using significant digits is also an important undertaking. My rounding rule usually follows a mathematical rule, which means if I have a 0.5, I round up. Anything below a 0.5, I was supposed to round down. Now let's take an example. Round the following to two significant digits. 2.46. You say, well, this is easy. I want to round this to 2.5. You're correct. What about 4.34? Again, round it to two significant digits. That's 4.3. I'm rounding down. What about 181? Again, rounding it to two significant digits makes this one 180. Lastly, what about 25.7? Well, if I round it to two significant digits, I'm getting a 26. Now, there is, however, in using significant digits in measurements, an interesting rounding rule. Unless a rounding digit is a 5, in this case, always round to the nearest even number. Okay, let's try that. Round the following two significant digits, 2.35. Well, in this case, it follows the mathematical rounding rule, and I'm rounding up. But what about 2.45? If I would round up, I would end up with 2.5. But the 5 would be odd. Hence, I would round this one down 2.4 because the 0.4 is the closest one that's even. What about 185? Again, if I rounded this one up, I would come up with 190, and that would be uneven. However, rounding down 180 gives me an even number for my rounding. What about 25.5? Again, where's the next even number? In this case, it's up, my 26, and the 6 would be even. Now, why this odd, well, actually even rounding rule when we're dealing with significant digits and in calculations? Let me give you a little thought example. Here is a list of 4 numbers. Now let's calculate the averages just the way they are. Let's forget for a minute about significant digits. Let's just calculate the averages of those 4 numbers. What I'm coming up with is 2.5775. Well, that's a pretty exact measurement. Now, let's do the following. Let's take our original numbers and round them to 3 significant digits, but using the mathematical rounding rule, which means 0.5 goes up, 0.4 goes down. Well, here's what I'm getting. 2.354 turns into 2.35. 2.745 into 2.75, 2.555 into 2.56, and 2.656 into 2.66. That is a typical mathematical rounding rule. Now let's take the average of this. I'm not looking here for significant digits. I'm just going to crank it out and see what my calculator tells me, and it would say 2.5800. Well, let's try our significant digit rounding rule, where we always round toward even. Here are the numbers. The first number would round to 2.35. The next number, however, would round down to 2.74 because 4 is the closest even number. The next number, 2.56, follows the mathematical rounding rule, and the next number, 2.66, also does it. Now, if we take the average of this, you can see an amazing result. It's 2.5775, not rounded to any significant digits, which means we have our original result of the averages as done in the beginning. Hence, the significant digit rounding rule helps us to mitigate false positives or false negatives if we take averages. Now, in conclusion, significant digits are only used and only useful when we do measurements and calculate with measurements. They are really not useful when we do mathematical calculations. But when we do measurements, we must follow the rules of significant digits.